Hello, my name is Alexis Ambries, and in this video I'm going to talk about a research paper that I did a review of called A Survey on Multimodal Large Language Models by Shukang Yin et al. So this is the table of contents, and this shows you the key points that I took away from the original article, and I separated them into 3 topics: ideological background topics, key technical topics, and additional MLLM techniques. And that means multimodal large language model, MLLM. So ideological background topics I covered were the interface framework idea and the idea of having mixed modalities as input and output. And the key technical topics were the architecture of the multimodal LLM and the data and training strategy used for different MLLM architectures. And then lastly, there's 3 topics that are additional MLLM techniques that are also commonly used even when you're not training an MLLM, and then you can apply these even in single data type kind of models that only use text or only use images, but are still used commonly. And these are in context learning, chain of thought, and the last one is kind of more specific to MLLM, and that's LLM aided visual reasoning. In context learning and chain of thought are general practices that you can use if you are building a neural network, and in this case these are MICL and MCOT because we are looking at multimodal models. So first we're going to look at the ideological background topics. And the authors, they reviewed general patterns and LLMs in this section. So it's not exactly them talking about exactly what researchers implemented or the technical details or specifically the kinds of data or anything like that. It mostly reviews general patterns, like what is these keywords that we're going to be looking at when we look at the MLLM architecture or the additional techniques. They explained a lot of that in their article. Since they covered a lot of topics, I think they wanted to do a good job at explaining what these background topics are, so they covered the ideas that underlies them. And so first I'm gonna look at interface frameworks, and these are commonly used by MLLMs for handling different modalities. For example, the authors identified that many MLLM systems contain a base MLLM that serves as a modality pivot. So this means the core LLM recognizes whether a request contains several modalities and then pivots the kind of processing that it wants to execute given that modality. So there are different modalities which are data types. So this could be like image or text or video or audio or something else. And then the LLM recognizes what it is and then shuttles it to alternative pre-processing steps and potentially other neural network agents, which we'll see in the LLM aided visual reasoning section, and they accomplish different tasks. And the core LLM basically serves as a delegator and a controller of the kind of steps that it will take, and in response to the original request. In mixed modality input and output section, I talk about alternative data types used by MLLMs to process requests. So this is a new idea that I'm going to look at because we're looking at MLLMs. So the data sets that are used to train MLLMs have a variety of modalities within them. So in general, when you look at a data set, usually it's only one type. But in a training phase for a MLLM, you can have one data set that has multiple data types linked in it, and they're all used at the same time during training. And the authors found that many researchers use a diffusion model that pre-processed all modalities into understandable tokens that can be processed by that base LLM. So in this technique, the diffusion model or diffusion module, you can think of it as another neural network whose only responsibility is to convert the data into tokens that is then used by the LLM. However, the diffusion model also is trained on its own data. So it's kind of like another layer of the model. So you can think of it as two models. However, in the paper, the authors note that it's attached to the base LLM, so you can think of it as a single model still, although it has two components. So the diffusion model can be understood to be its own neural network, but it translates the modalities into a natural language token that is then interpreted by the larger core LLM. So this is how you would input the mixed modalities and then have the model be able to recognize it and then use it for outputting LLM responses as text. In the next section, I'm going to talk about key technical topics, and these are not the ideas like I just covered. Like, these are specific details that the authors reviewed that are common in MLLM research that they reviewed. And first, I'll talk about MLLM architecture. This is the common neural network building patterns for MLLMs. The authors found that most MLLMs utilized a base LLM, modality encoders, and modality interfaces. So I covered what is the modality encoder, and I covered what is a modality interface, and what is the base LLM. And then these are all coming together in the neural network architecture. They found that transformer-based architectures were trained to answer general queries in natural language. This is the base LLM. So if you are using a diffusion model, the output is going to be text because the base LLM is trained in text and only outputs text. However, it can still use as input images and other kinds of data. It can recognize it, but it doesn't know how to output image or output audio. It only knows how to output text. And then the encoders are the diffusion models that use the different kinds of modality or data types and then encode them into various modality tokens. So you can have many of these for every kind of modality or combination of modalities. And then they all send their tokens back to the base LLM, and then the base LLM responds. And the modality interface is the kind of connection that the LLM uses to connect to the encoders or the diffusion models. So it would recognize that there's different data types, and then it would then use the interface to connect to the diffusion models and receive back the tokens, and then kind of combine everything if there's many data types, and then make a single response. So you can think of every modality encoder as a different task in a way, because it is converting the original request into tokens, and then it's coming back together to the base LLM for that original request. Next, I'm going to talk about the data and training strategy for MLLMs, and these multimodal data sets have their own challenges. As I mentioned, usually a data set has one kind of data. It can be just text or numbers. They are still text in a way because it's all like in its own data. However, if you have images or audio, you can't really have that in a regular data set like you would say in an Excel sheet. So these kinds of data require different data structure requirements. So multimodal models that use these data sets to train require many phases in training, so as they incorporate many combinations. So since they are complex, it's necessary to monitor the data set granularity according to the authors, which is whether the data has general or detailed features. You can monitor their ability to support multiple languages and to contain domain-specific knowledge for the tasks that you are targeting. Since you usually only want to train a few times rather than many times, since you have a large amount of data and it's very complex to store, and you're training a model, you don't want to spend too much time training a model using one data set that's really large and contains complex kinds of data. So it's very important that if you're training, you start with a really good data set so that later on you don't have to make a change to the data set and then have to retrain, because then it's going to take you forever to retrain it again if you made a change to the data set, or you know that the data granularity is very general and you want more detailed features, or you're missing a language and then you want to add another language. It's going to have to meet those requirements originally to avoid having to retrain. And an example to improving the data for model training in this way that the authors found is that a lot of researchers, for example, using image and text multimodal data, is they were able to add interaction for users during training by segmenting the image that was used as the input using bounding boxes, and then offering the user, after training, the choice to specify the specific segments within the image they would like the model to refresh when they're conversing with the model in their memory. So after training, since you have already segmented the image, then the user can just say, oh, top right of the image is where I'm more interested in. It would automatically recognize what is top right, because during training the image was segmented and paired with a text description of which side of the image, so that you don't have to go back and train using extra data, having the bounding boxes. If you already included that originally, then it would have that ability post-training automatically. Additional MLLM techniques that the authors reviewed for model building are also common even when you don't have multimodal data, and are also common in LLMs. However, one that was unique to MLLMs that they covered was LAVR, or LLM-aided visual reasoning. So first I'll talk about the first two, which is in-context learning and chain of thought, which are common in neural network building techniques, and these improve the responses of the model. In context learning, or MICL, the authors note that it is useful when you have a large amount of data and it's difficult to retrain the model, as I just mentioned. And usually this is common in multimodal models because they have large amounts of data and it is very complex. And they note that a lot of researchers realize that, and they applied MICL when training a lot of the time because it is very useful for improving the model's responses without retraining. So if you want to add another feature or like another capability to the model to target a different task, you don't have to retrain it exactly or fine tune it. You can just apply MICL. MICL is able to improve the response by using a template when inferring. So when you're already calling the model, you use a prompt and it has a template with examples of accurate responses in the text format. And since you're using multimodal data in MICL, you would have examples that contain the kinds of data that you want the model to be able to interpret. So you would have to format it for images, or you would have to format it for audio and text. And finally, the authors note that care should be taken to utilize templates having many types of input data within the prompt, since it's multimodal ICL. In multimodal chain of thought, it is also similar to ICL because it's not applied during training, it's applied after training. So this is also useful for multimodal models because you don't want to have to retrain again just to add some extra task or extra fine-tuning. You don't want to do that, so you can just apply chain of thought and it would improve accuracy in a way. So it's useful in cases even when you're not using multimodal model. Chain of thought is still useful even when you're just using text. The general idea or principle is that this technique allows for the model to think through difficult problems using a mental scratchpad. So it responds in multiple subqueries. It kind of decomposes the original question, recognizes that there's different facets to the original question, and then pulls it together and answers each section and then combines it. And in MLLMs, usually chain of thought is usually paired with a model that is trained with a few or zero-shot training, which means they implemented basic ICL or no ICL, like I just mentioned. So that means that it receives the input and doesn't really process the input from the user and then passes that to the model without applying a template. So the reason why they do that is because in chain of thought, you usually want to have multiple chains or at least a single chain before you decompose the original input. So in the case with multimodal models, you don't want to have multiple chains in a way because it will require a lot more computation since it's complex data, and the template would also be complex before you pass it to the model, meaning there's going to be more memory usage and it's going to take longer to respond. So multimodal models usually apply chain of thought using the single chain method, where it still applies it. However, it's a little bit simpler than other chain of thought methods that single modal models like single LLM models use. Nowadays, they use Markov decision tree chain of thoughts, where they have multiple chains of thoughts going at the same time, and then they can go back to earlier splits in the chain if they decide that they need to go back because they reached a inconclusive answer. And that's why when the researchers looked at chain of thought, they found that the only paper that they did find that implemented the decision tree chain of thought was called duty distinct chain of thought for handling the different kinds of modals. But usually they just use the single chain method. And then finally, I'm going to talk about LLM aided visual reasoning, or LAVR. And this is the more complex technique that they found that MLLMs usually use when using visual data. And the authors note that the LAVR technique is good because it applies strong generalization, such as finding hidden meaning in images, such as in memes, and it provides interactivity and control to users. And LAVR is in essence a multi-agent system or multimodal system that has multiple models. As I just mentioned previously, usually MLLMs have one model that has multiple data as input, and then it has like a diffusion module that kind of interprets all of the data and then combines it into a token or into multiple tokens having those data, and has one input and output point, which is the base LLM. However, LAVR has multiple models that are fine-tuned for different modalities. And in the LAVR technique, they have visual models trained for different tasks for the visual modality. And this is an improvement to the original method, which is using the single base LLM with a diffusion module, because the base LLM is serving as a all-rounder and handles all the data from all the modalities using its text tokens, and is more general when using LAVR because you have multiple models fine-tuned for different tasks, and then it can apply or it can pre-train on more data tuned for different kinds of images. So if you separate the modalities as opposed to having a single multimodal model and have a multi-agent system using LAVR, which is an improvement over just having the diffusion module, then you can have an interface that connects them, and it allows for the LLM to act not only as the task delegator, as I just mentioned, but it also works as like a decision maker and semantics refiner, because now is not only separating the modalities to different diffusion models and then uses those as input, it also receives extra reasoning from those models because they are more fine-tuned on those modalities. So it can make better decisions by combining them, and it can enhance the reasoning that they provide because it is trained on more natural language data as the LLM and can refine their semantics. So that is my presentation for MLLMs and the research survey that I reviewed. Thank you.